Hi, so this video is going to cover section 4.4, exponential and logarithmic equations, right? So far we've, looked at what a logarithm is. We looked at some different types of logarithms, so logarithms with just a generic base b, some logarithms with base 10, right? We call that the common logarithm. And then we also look at the natural logarithm, ln, where the base is Euler's number, e, right? The natural number. So we've looked at that. We've looked at some properties of logs, right? So we've kind of been setting ourselves up so that way we can begin to solve exponential and logarithmic equations, right? So the first type of equations we want to look at are exponential, right? And I have here just a snippet from the textbook, right? So an exponential equation is an equation containing a variable and an exponent, right? So there are some examples there of some exponential equations, right? So we want to be able to solve for that. And the fact that we're going to use is this idea that exponential functions are one-to-one, right? So that means that two different ordered pairs, have two different ordered pairs have to have the same second component, right? So in other words, if we have like the same if we have the same output, we have to have the same input, right? The x and y's, they have to match. They can't be different, right? So if I put, x equals 1 in the equation, I only get just one output, right? And also for every y value, there's only one associated x value, right? That's what I mean by one-to-one, right? So by knowing that, if b to the m equals b to the n, then their exponents must be the same, right? So that's just listed here. And then again, seen in this this box, right? I've actually presented this before. I know I presented it earlier in class, and I just presented it in the previous video. I think I used a to the u equals a to the v, right? But the same idea, just different letters, right? It's the same exact thing, right? So if you have an expression where, both sides are equal and both sides are represented as a power of the same base, then their powers, their exponents must be the same, right? So we can use this idea to help us solve some special types of equations, right? So those can be solved if you have the same, if you can write both sides with the same base, right? So here's two examples of that. Like if we, looking at part A, on the left we have the base of 2, and 16 turns that I can rewrite that as base 2, right? 16 is equal to 2 to the fourth power, right? So we can use that idea to rewrite the right side, right? So when I have 2 to the 3x minus 8 equals 16, I can, instead of writing 16, I can write 2 to the fourth, right? Because 2 to the fourth power is equal to 16, right? So by applying that rule that we use, right, we have a statement where we have the same bases on both sides, so their exponents must be equal, right? So this means that 3x minus 8 must equal 4, right? So then I can solve for x, so I can add 8 to both sides and get 3x equals 12, divide both sides by 3, and I get x equals 4, right? So x must equal 4. Right, so when x equals 4, we're going to get the same exponent on both sides for the bases, right? So in part B, right, what you should be recognizing is that 27 is 3 cubed and 9 is 3 squared, right? So I can rewrite both as a base b, or excuse me, base 3. So instead of 27, I could write 3 cubed and that whole thing is being raised to the x plus 3 power. Right? So just replacing 3 cubed for 27, and I can replace 3 squared in for 9, and that's being raised to the x minus 1 power. Right? So now, since we have power to a power, I can simplify this to get it in the form that I would like by multiplying the exponents. Right? So this would be 3 to the 3 times x plus 3 equals 3 to the 2 times x minus 1. Right, so that's the power to power rule, right? And we reviewed that in the last section. We looked at properties of logs. We reviewed exponential rules, or some common exponential rules very quickly. Right, so power to a power, we multiply. Right, for the exponent rule. Right, so this means 3 times x plus 3 must equal 2 times x minus 1. Right, so then I can work with this and get 3x plus 9, so just distributing on the left and on the right, we get 2x minus 2 on the right, and then solving for x, right, I can subtract 2x from both sides, and we'll subtract 9 from both sides. So that's gone, I'm left with x equals, so negative 2 minus 9 is negative 11. Right, so that would be the answer for part B. Right. So then checkpoint 1 is 2 similar examples to what we just did. So maybe a good technique might be to maybe pause the video and try to work through those on your own, and then you could hit play and just make sure you can get the same answer that I do, right? Right. So for part A, the important thing to note is that 125 equals should be 5 cubed, right? So what we would have is 5 to the 3x minus 6 equals 5 cubed, right? So now I have it in that form, right, that I'm looking for, with the same base, and the exponents, must be equal that form. Then these exponents must be the same, right? So 3x minus 6 must equal 3. We need to solve for x. So we get 3x equals 9. Divide both sides by 3. I get x equals 3. Right? So part B, what the trick to this one is 2 cubed is 8 and 2 squared is 4. Right? That's going to be our trick to get these to be the same base. So we would have 2 cubed raised to the x plus 2 power equals 2 squared raised to the x minus 3 power. Right, so just like before, we need to multiply, right, using the power rule for exponents. So this would be 2 to the 3 times x plus 2 equals 2 raised to the 2 times x minus 3 power. Right, so this means that their exponents must be equal. 3 times x plus 2 must equal 2 times x minus 3. So distributing, we get 3x plus 6 equals 2x minus 6. Right, so I can subtract 2x from both sides, subtract 6 from both sides. We get x equals minus 12. Right, so there's solutions for part A and B. Right. So now what we can do, another trick. So if we're not able to rewrite both sides as the same base, right, which is probably likely, that was a special case. What we can do is use logarithms to solve both sides. So we're going to use that power property of logarithms in order to get that exponent out of the get the variable out of the exponent, right? So the general idea is that you can take the logarithm of both sides of an equation, and it remains equivalent, right? Now you have to take the, to the left and right sides. Both sides have to have the same base, though, right? That's the understanding. So when I do this, I like to just use natural log because it's less to write, and it just seems to make it easier for me. So for part A, how I would approach this, we have 4 to the x equals 15. So you can see step 1 is you want to isolate the exponential expression, right? So if we had like a plus something or something times, like, I don't know, maybe like 2 times 4 to the x, you'd want to get rid of all that stuff, right? So for part A and B, these are, maybe some simpler examples. We're going to work our way up to some harder examples. Both of those are already in that form for us, right? So once we have it in that form, what we can do is take, as I was saying, the log of both sides, and this remains equivalent expression, right? So then now I can use that power rule and pull that exponent out front. So then what we would get, on the left-hand side would be x times the natural log, times the natural log of 4 equals the natural log of 15, right? So you can see now that I have, it's easier to isolate the variable, right? Because when you see the log of some number, as I pointed out before in preparation for this, is that this is just a number, right? So this guy is just a number, some constant number. This is also a number, right? So you can think of it as like, what if this was like square root of 10, right? That's just a number, right? Same with this. This is just a number, right? The natural log of a number is just a number. Where like if we had like square root of x, right? This isn't necessarily a constant, right? It's going to change depending on what x is, right? So similarly, if I had like the natural log of x, then that wouldn't be, just a number, right? But the natural log of a number is just a number. So in other words, I have a number times x equals some number. So how do you solve for that, right? So just like if I had, 2x equals 7, right? I would divide both sides by 2. Same idea. I'm going to divide both sides by the natural log of 4, right? So then what I end up getting is x by itself, right? Because this just reduces down to 1, equals the natural log of 15 divided by the natural log of 4. Right? So that this is the exact answer, right? And we could get an approximation using a calculator, right? So if I pull that over, right, we could just take the natural log, the natural log of 15 parenthesis divided by the natural log of 4, right? Close parenthesis, and we get that, right? So roughly we get 1.9534, right? If we went around to 4 decimal places, right? And if you think about this for a moment, right? So x was approximately 1.9534. If we think about, is this reasonable? Well, it seems reasonable because 4 squared is 16. Right? So if I raise 4 to some power to get 15, I know it should be less than 2, but it should be pretty close, right? So it seems reasonable, right? My answer seems likely, right? So you can kind of use that just basic number sense just to make sure, we didn't make a silly error somewhere. All right, so let me erase this. I'm going to do part B in a different color. Right. So with part B, we have 10 to the x equals 120,000, right? And in the book, if you have a base 10, they recommend you just use the common logarithm. Maybe it'll, I think what they're hoping is maybe it'll, reduce down or simplify kind of nice, but I don't know. I just stick with natural logarithm. So, we want to get it in this format first, right, which we already have it in that form. And then I'm just going to take the natural log of both sides. Right? And then using, a property of logarithms, the power property, I can pull that exponent out front. So we get x times the natural log of 10 equals the natural log of 120,000, right? And then I can divide both sides by the natural log of 10. And I'm left with x equals, the natural log of 120,000, all divided by a natural log of 10. Right? So that's an exact answer. And I could actually make this a little nicer, because one thing you'll notice is, I could rewrite the right-hand side to be the natural log of 120,000 divided by 10. So then this would become the x equals a natural log of 12. It'd be 12,000, right? Because we would just get rid of one of the zeros when we divide by 10. So I don't know. That may be a little nicer, but I don't know. I mean, for me, I'm perfectly fine with getting this solution as an exact answer. So then we need to approximate, right? Maybe get a decimal approximation. So if we take the natural log of 120,000 divided by natural log of 10, we get 5.079. And then notice if I take the natural log of 12,000, I should get the same answer. All right, so so to get an approximation, I can just take the natural log of 120,000, right, divided by the natural log of 10, and I get roughly 5, right? 5.0792 if I round to 4 decimal places, right? So x is approximately 5.0792, right? So just to be clear, this is an exact answer, right? This is an approximation, right? So just like over here, right? This is my approximation. This is my exact answer, right? So those are two different types of answers that we might have to show our work in, right? So then again, you could think about, is this reasonable, right? So, 10 to the 5th power would be 1 with 5 zeros, right? So that would be 100,000. So, it seems reasonable, right? Because, 100,000 is, fairly close to 120,000, and 5 is fairly close to 5.07. So, yeah, that seems reasonable, right? We seem in the ballpark that my answer would be correct. Right, so now we want to maybe try to increase the difficulty a little bit. So if I look at this next example, example 3, notice I have a number times my base with an exponent minus another number equals 237. So the first thing we want to do is isolate this e raised to the exponent, right? I want to solve for that. Right, so probably the first thing you'd want to do is add 3 to both sides. So we get 40 times e to the 0.6x equals 240. And then next, I would divide both sides by 40. So then we get e to the 0.6x equals, 240 divided by 40, that would be 6, right? So then now is where I could take the natural log of both sides. So then what I end up getting is 0.6x times the natural log of e, right, equals the natural log of 6, right? But you should note that natural log of e is just 1, right? So this would just be 0.6x equals the natural log of 6. So then I could divide both sides by 0.6 to get x by itself. So we get x equals the natural log of 6 divided by 0.6. And this is approximately equal to 2.986. Right? So you could check that in your calculator really quick. The important thing here to note is you have to close your parenthesis, right? The natural log of 6, right? And then we're dividing that by a constant. So it's not taking the natural log of 6 divided by 0.6, right? Taking the natural log of 6 and then that whole thing divided by 0.6, right? So we get that as a solution, right? So then, right, so the whole trick, right, is being able to get like this by itself, right? That exponential expression, the expression with the exponents. Right? So then if we look at this example, we have 5 to the x minus 2 equals 4 to the 2x plus 3. So this particular example is going to be maybe a little messy, but not too crazy. So it's already in that like exponential form, right? On the left, I have a base raised to an exponent. On the right, I also have a base raised to an exponent, but it's different bases, right? So their exponents aren't going to be equal to each other, right? Because we have different bases. So what we want to start by doing is, taking the natural log of both sides, right? And remember, the whole idea with that is to be able to get those variables out of the exponents positions, right? So then now I can rewrite by taking those exponents out front as a factor, right? So this would be x minus 2 times the natural log of 5 equals 2x plus 3 times the natural log of 4, right? So you want to be careful with this in the sense that we're going to have to distribute, right? This is a number times a difference, and this is a number times a sum, right? So that's just like distributive property, right? That's just like if I had 5 times a plus 6, right, or something like that, right? We'd have to distribute the 5 through, right? So that's what we'd want to do next, right? Because we're trying to isolate x by itself. So this would give me the natural log of 5 times x minus 2 times the natural log of 5. So this is especially where you're going to want to be really careful with the notation in terms of closing our parentheses, right? So we really clearly understand exactly what we're doing. And then on the right hand side, we would have 2 times the natural log of 4 times x plus 3 times the natural log of 4, right? And just to be really clear, right, this is just a number. This is a number. This is a number, right? Not the x. Didn't mean to go under that, right? And this is a number. So this might look really scary, but really it's just like something like this: 2x minus 6 equals 5x plus 4, right? This is a similar type of equation, right, as this, right? They don't necessarily have the same answer. They're not equivalent, but they're similar type, like how they look. So don't be super scared off by the notation, right? We want to get x by itself, just like we normally would, right? Just like in the green. So what I would do is subtract 2 natural log of 4x from both sides, right? And then that means that we want to add 2 natural log of 5 to both sides, right? Because that will cancel and that will cancel, and I'm left with just something times x on the left hand side and then equals some number on the right. And then I can divide by the coefficient and get the solution, right? Just like we would any old equation. So then what I'll have on the left-hand side is the natural log of 5 minus 2 times the natural log of 4, and this is all times x, right? Because when we subtract, right, we subtract their coefficients, right? So that's why I'm subtracting the amounts times x. And then this would be equals, and then we would have 3 times the natural log of 4 plus 2 times the natural log of 5. Right? And again, this is just one number on the right-hand side. Right? And then now I have a number times x equals some number, so I'm going to want to divide by the number being multiplied by x. Right? So if we divide both sides by the natural log of 5 minus 2 times the natural log of 4, then we get x by itself. So x is equal to 3 times the natural log of 4 plus 2 times the natural log of 5, all divided by the natural log of 5 minus 2 times the natural log of 4. Right? So that is x. This is the exact answer. Right? So we can get an approximate answer, right? So we would do, begin parenthesis, right? We'll put the numerator and denominator in parentheses separate. So this would be 3 times the natural log of 4, close parenthesis, plus 2 times the natural log of 5, close parenthesis, and then I need another close parenthesis for the numerator, and then divided by, and then open up a parenthesis for the denominator, natural log of 5, minus 2 times the natural log of 4, close parenthesis, enter, and we get a decimal approximation, right? So a decimal approximation for this would be negative 6.34, right? So x is approximately negative 6.34, right? So here's my approximation. All right, so that one might seem a little intense. I think the tricky part is just the notation. So you want to make sure you practice that. Right? All right, so in this example, we're going to use something called U substitution. So sometimes we use this in algebra, but if you take calculus, you're going to use it a lot in calculus as well. It's a nice technique to maybe make something complicated less complicated, right? Just by replacing something with u or a different variable, right? So one thing that you want to notice about this equation is e to the 2x is the same thing as e to the x times 2, right? So e to the 2x equals this, which is the same thing as e to the x squared, right? So it's like doing the power rule, but in reverse, right? So really this equation is e to the x squared minus 4e to the x plus 3 equals 0, right? Well, this looks somewhat, similar, right? So this might, kind of be in the form like x squared minus 4x plus 3 equals 0, right? And we know how to solve that equation, right, really well, right? But something you'll notice is we already use x as a variable, so it'd be really confusing if I substituted, e to the x for x. So that's where, maybe we'll use u substitution, right? So, we kind of have it in that form, but that's not exactly what we want to do, right? So how you do this is we're going to say, let u equal e to the x, right? So by letting u equal e to the x, and the fact that we know this is true, right, that e to the 2x is the same thing as e to the x squared, then my equation that I would have would be, it'd be, e to the x quantity squared minus 4 times e to the x plus 3 equals 0. And we're going to substitute u in for e to the x. So this would become u squared minus 4 times u plus 3 equals 0, right? And this actually will factor. This will factor into be what, x minus 3, or excuse me, u minus 3 and u minus 1, I believe, right? U minus 3 and u minus 1, right? Yeah, that works, right? Because you'd have u squared minus 3u, and then minus another 1 will give you minus 4u, and then negative 3 times negative 1 gives you the positive 3 that we're after, right? So in other words, u is going to be equal to 3, or u equals positive 1, right? We know this to be true, right? Because we solve each of these for 0, right? So if you wanted to write this out a little more formally, we would say u minus 3 equals 0, or u minus 1 equals 0, right? And of course, you would solve each of these, and that's where you get u equals 3, or u equals 1, right? All right, but we weren't after what u equals. We were after what x equals, and we just used u to kind of as a way to help us get the solution, right? So u was e to the x. So really, what this means is that e to the x is going to equal 3, or e to the x is going to equal 1, right? Because this is just u, right? So now I can use that information to help me solve for x, right? So I could rewrite this e to the x equals 3. I could rewrite that in its exponential form, or excuse me, this logarithmic form. That would be the natural log of 3 equals x, right? Or this would be the natural log of 1 equals x, right? And we should know that the natural log of 1 is just 0, right? So this means that x equals 0, right? So the solution set for x would be the natural log of 3 and 0, right? So there's two potential answers for x, natural log of 3 and 0, right? All right, so far we've been looking nothing but exponential equations. Now let's look at logarithmic equations. So we're told here that a logarithmic equation is an equation containing a variable in a logarithmic expression, right? And we have some examples of those, right? So you can look at those. So some logarithmic equations can be expressed in this form, where you have log base b of m equals c, and you can solve those by rewriting those in exponential form, right? And you can solve for the missing variable, right? So that's what we want to practice now, right? And again, this is like a special kind of case, so it's just giving us some techniques to help us solve these, right? So for part A, right, we already have log base 4 of x plus 3 equals 2. So I could go ahead and rewrite this in exponential form. So that would be 4 squared, right, equals x plus 3. Well, we know what 4 squared is. That's 16, right? So then I could subtract 3 from both sides and get x by itself. So x would equal 13, right? And just like you've learned all throughout algebra, we can take x equals 13 and plug it into the logarithm and check our answer, right? So in other words, if we take log of 4 of 13 plus 3, we hope to get 2 back, right? Well, that means that 4 squared equals 13 plus 3, which is true, right? This would be 4 squared equals 16, which is true, right? So it works out. We would get 16 equals 16, right? Also, another thing to keep in mind is what's the domain of the log. So we've done this a few times before, because if we get an x value that's not in the domain, we have to throw that out, right? It's called like an extraneous solution. So in this case for part A, the domain would be, so we want x plus 3 to be greater than 0. So if I subtract 3 from both sides, we get x must be greater than minus 3, right? So that's the domain for part A. So it might be helpful, to maybe start with that, because then when you get your x value, if you get something that's not in the domain, we just need to throw it out, right? So here for this one, we have 3 times the natural log of 2x equals 12. So the first thing I would want to do is we want to isolate that natural log, expression, so I could divide both sides by 3. So we get the natural log of 2x equals 4, right? And then now if we, look at this, the domain would be, we want 2x bigger than 0, right? So that means we want x greater than 0, right? So again, if I get an x value that's equal to 0 or less than 0, in other words, not greater than 0, that's not going to be a solution, right? So then I can rewrite this in exponential form, right? This would be e to the 4th power equals 2 times x, right? 2x. And then I could divide both sides by 2 and get x equals e to the 4th divided by 2, right? And don't forget, e is a number, right? It's just like pi, right? It's just a symbol we use for that irrational number, right? So that's the exact solution, right? And of course, you could plug that in your calculator and get an approximation if you were asked, or if you wanted to have that, right? Excuse me. All right, so in this next example, something that's important to recognize is that on the left-hand side, I have 2 logarithmic expressions, but we're going to want to condense those down into just one logarithmic expression, right? Because that's like, if you look back at that table, I didn't really go over it, but if you like, following like a list of steps to do for solving an equation, I give those for those students that enjoy those. It just walks you through, maybe step-by-step suggested steps on how to solve one of these equations in general. So that's like the first step, right, is to be able to get just one log expression equals, something without a log on the right. Well, as long as it's not like a log of a variable, right? If it was like log of like 5, that would just be a number, so that would be okay on the right-hand side, right? But we don't want to have log of a variable on both sides, right? We want to just have one of those equals some like number on the right, essentially. So what I can do is I can combine both of those, right? Because I have the same base and we're adding, so that means it's the log of the product, right? So this would become log base 2 of x times x minus 7 equals 3. Right, so then, something just quick to denote would be the domain, right, of each of these. So like of this first one, we need x bigger than 0, right? And then for this one, we need x minus 7 greater than 0. So that means if we add 7 to both sides, x has to be greater than 7, right? So really what we're after is we need all values to be, all solutions to be bigger than 0. If they're not, then they're not going to fit into being able to be plugged in, right? Or excuse me, we actually need, in order for both to work, right, we need x values bigger than 7, right? That's the intersection, the common part, right? So if you have trouble seeing that, if I make a number line, here's 0, here's 7, x greater than 0 would be an open circle at 0 and then shading to the right. but then x bigger than 7, I'll use a different color, would be an open circle, then shading to the right. So this is the overlap part, right? So I'm going to want all x values to be greater than 7 then, right? So if you look at each of those individually, you want to take like the intersection, right? Right, because like let's say I plug in x equals 1, this log is fine, but if I plug x equals 1 into this, then what we're taking the log of is negative, which can't be it's not in the domain, right? So that's just quick review of what we looked at before. We looked at some of those, right? So then back to this problem, right? If I rewrite this in exponential form, I would have my base is 2, so it'd be 2 to the 3rd power equals x times x minus 7, right? So then what we have is 8 equals, and then this would be x squared minus 7x. So this should be in a very similar form, right? This is just a degree 2 polynomial, right? So, a way to solve that is to set one side equal to 0, and then we can maybe factor this or use the quadratic formula to find values for x, right? So this will actually factor. It's what x minus 8, x plus 1 works, right? So in other words, x is 8 or x is minus 1, right? So then you could, so now what we need to do is check to see if both of these will work, right? So remember, I said that x has to be greater than 7, so this one's good, right? Let me change color. So this one's good, but this one's not, right? Because it's not bigger than 7. So the solution set is just going to be, 8. Right? That's the possible x values, right? So x equals 8 is the solution, the only solution, right? So remember, this is called an extraneous solution, right? So it's an extra. It doesn't actually work for our equation. Right, it's kind of like before, if we would get like negative time or something, right? And you would throw that out. Same idea. It doesn't fit in our domain. Right? All right, so now what we want to do is looking at another type of equations. And this is using what's called the one-to-one property of logarithms, right? And we've already mentioned that. But essentially, what we're trying to get after is if you have a function, an equation that looks like this form, so you have the log of some base of m equals the log of that same base of some other expression, then that's going to imply that m equals n, right? So it's kind of doing, when we were taking the log of both sides, it's kind of doing that in reverse, if you will. Right? So if, right, and it's making sure it says, check proposed solutions in the original equation, include the solution set only values for which m is greater than 0 and n is greater than 0. Right? So we need each of these pieces to be bigger than 0. Right? All right, so if you want to start maybe looking at the domain, right, the first one, right, the first one we're going to want x plus 2 to be greater than 0, right, and then we're also going to want 4x plus 3 to be greater than 0, and we also want 1 over x to be greater than 0, right? So just taking each of these parts, putting them greater than 0, and we want to find like what's common between all of them, right? So for the last one's pretty easy, right? This one will always be greater than 0. So x could be X could be any number, well, except for X can't be 0, right? So this case just implies that X cannot be 0, right? Because we can't divide by 0. But if I plug in any other number into this, excuse me. It can't be negative, right? Because if I take 1 divided by a negative number, that's going to be less than 0, right? So I don't know what I was thinking. So in other words, X has to be bigger than 0 in this case. So as long as X is positive, then we're good, right? So for that last logarithm, right? So if I work with this one, right, if we subtract 3 from both sides, I would have 4x greater than minus 3. So I could divide both sides by 4, and that gives me x greater than negative 3/4, right? And then this one, if I subtract 2 from both sides, that gives me x greater than minus 2, right? So these are kind of like my 3 constraints for x. So if I look, if it helps, if you're a visual learner, if we want to draw this really quick, negative 3/4, and then over here, we'd have 0. Then we're going to want this part to fit all of our categories, right? Because if I pick a number less than 0, it's going to fail this condition, right? So you always pick like the right, kind of like the rightmost part, if you will, right? So in other words, x has to be greater than whatever that biggest number is, and the biggest number between -2, -3/4, and 0 is 0, right? So and if that's not 100% clear, let's say I pick a number greater than -2, like -1. If I plug that into here, that would be the natural log of 1 over -1, which is the natural log of -1, which is undefined. We can't find that, right? Because that must be greater than 0. So that's where it all falls apart, right? So you just really need to pick like the biggest one, right? So our condition is that x must be bigger than 0, right? So if we get a solution that's not bigger than 0, we got to throw it out, right? So that's an important first step, right, as I was saying. So they do it a little different. In the book, like where it says 0.4, they recommend that you take those solutions and plug it into each of these and see if any of those will give you a value less than 0. And if it does, you have to throw it out. So that's perfectly fine as well, right? You could do that. I'm just thinking about this maybe a little differently than the text, right? Which is a good thing, right? Be able to get some different viewpoints. All right, so now let's try to solve this. So first thing I can do is I could rewrite the left-hand side of the equation and make it just one logarithm, right? Because we practice all this, right? So this would be the natural log of x plus 2 over 4x plus 3, right, on the left, equals the natural log of 1 over x, right? So then now we're using the property presented, right, which is here circled in red, right, which is right there. So we have this setup right now with the same base, right, both base e. So this means that these two things are equal without the logarithms as well, right? So x plus 2 over 4x plus 3 must be equal to 1 over x, right? So then if I multiply, so what I could do is just, kind of set up like a proportion, like, maybe you've done in like middle school or before then. So we could just cross multiply here, right? So in other words, this would become, x plus 2 times x equals, 4x plus 3 times 1. So I just won't write that. I'll just leave it as 4x plus 3. Right? So that's one way to do it. Or if you, I don't know, maybe a little more mature way to think about this is multiplying both sides by the least common denominator, which would be x times 4x plus 3, right? So if we were to multiply both sides by that, that would also get us to this, right? That's why cross multiplication works. Right. So then, but cross multiplication is perfectly fine, right? You can do that. So then we would have, x squared plus 2x on the left equals 4x plus 3. So we have a degree 2 polynomial. So, like we've done a million times, we want to set this equal to 0. So I can subtract 4x and subtract 3 from both sides. So we're left with x squared minus 2x minus 3 equals 0. This will factor x plus 1 and x minus 3, right? So, that means that x plus 1 equals 0 or x minus 3 equals 0. So if I subtract 1 from both sides here, we get x equals negative 1. And then here, if I add 3 to both sides, I get x equals 3. Right? So one of those looks to be the solution, right? But remember, in checking our conditions, we said that x, this condition x had to be bigger than 0. So this one gets thrown out, and that's the solution, right? So x is equal to the set with just 3 in it, right? That's the solution set. Oops, that's a bad setup there. Good. All right. So now ready to talk about maybe some applications. So I have just two examples left. Oh, I have more than that. All right. So we can get through this, right? So then the next problem application, example 9, is called alcohol and risk of a car accident. So it says medical research indicates that the risk of having a car accident increases exponentially as the concentration of alcohol in the blood increases. The risk is modeled by this function, right? So of course you would imagine the function would be an exponential or logarithmic equation. So we're told some more where x is the blood alcohol concentration and r is given as a percent. And is the risk of having a car accident. So it says what blood alcohol concentration corresponds to a 17% risk of a car accident. How is this shown on the graph of R? Right? So what we would have, we would plug in, R equals 17 and into the equation, and we want to solve for x essentially, right? So we would have 17 equals 6 to the e 12.77 times x, right? So just like we've done before, we want to get the exponential by itself, so divide both sides by 6. You get 17 over 6 equals e to the 12.77 times x. And then now, just like before, where we can take the natural log of both sides and be able to get that exponent, that variable out of the exponent, right? So the right-hand side would just be the exponent, right, because that's a cancellation property. And then this would be the natural log of 17 over 6. Right? So of course, to get x by itself, I would divide both sides by 12.77. And we get x equals the natural log of 17 over 6, all divided by 12.77, right? And so that's my exact answer. I can get an approximate answer, which is 0.08, by plugging that in my calculator, right? And then we were asked to look at the graph of this, and I have a graph listed here, right? So you could read over that, but this point, is a blood alcohol concentration of 0.22, which corresponds to near certainty or 100% probability of a car accident, right? So that's that point. So we were, the point that we found was we were looking for 6%. Right, so we want the y value, that's 6%, and 17% risk. Right, so our point would have been, somewhere in here, right, in between 0.5 and 0.10 for the x coordinate, right? So that's what the graph looks like of that function, though. So it's exponential, grows really quickly. All right, so then the next example is an application with money, right? So I don't know, I think the compound interest and exponential functions, it's real, there's a lot of applications within terms of money, right? And especially as you maybe start to buy your own home and stuff, that's going to, be of more interest to you when you're trying to, become more debt-free and more independent, right? So, right, we're given the formula for compound interest, right? So we have that and define all the variables, which we already know. We've used it before. So we're saying how long will it take $25,000 to grow to $500,000, $500,000, if you have a 9% annual interest compounded monthly, right? So we have this account. We want to throw 25 grand in there, and I want to know how long will it be till I have $500,000, right? So this is maybe a classic example, maybe thinking about like a retirement fund, right? Because everyone wants to be a millionaire at some point, and everyone will as long as you're responsible and have a retirement plan. You'll have at least $1 million saved up in your retirement fund, right? So if we plug in what we know, so we want the amount to be 500,000, right? That's going to be A. That's what we want in the end. P is 25,000, right? That's the principal. It's our initial value, what we're putting in. And then inside of here, we'd have 1 plus, and then my interest rate's 0.9, right? So I'd put in 0.09. And then my N value is 12 because it's compounded monthly, right? And then my exponent would be 12t, right? Because n is 12 again, right? So this is just plugging in what we know into the function. Now I want to solve this for t, right? Notice it's an exponent, right? So we want to try to solve this as much as we can. So the first thing I would do is, we could simplify this pretty easy, right? So if it should come out pretty easy. So if I take, 0.09 divided by 12, we get 0.0075, right? And if I add 1 to it, you of course get 1.0075. So that's what the expression is inside the parentheses, right? Now this might not always come out real nicely, so you might have to leave it alone, right? So for example, if this was like 1 plus a third, that has a repeating decimal, right? It's going to keep going on forever. So you won't end up getting an exact answer if you do it that way. But the reason why I can plug this in is because this expression in parentheses is exactly equal to this number, 1.0075. It has a terminating decimal, right? It's not doesn't have like a repeating block. So I could rewrite this as 500,000 equals 25,000 times 1.0075 raised to the 12t, right? So maybe it just makes it a little nicer to work with. And then I could divide both sides by 25,000, because remember, I'm trying to isolate this part, right? So I can take the natural log of both sides. So 500,000 divided by 25,000 is 20, right? So the left-hand side should be 20, and this is equal to 1.0075 raised to the 12t. So now what I can do is take the natural log of both sides, and then what that allows me to do is take this exponent out front as a product, right? So that would give me the natural log of 20 equals 12t times the natural log of 1.0075. And then we want to solve for t. So I'm going to divide both sides by 12, natural log of 1.0075. Right? So then, this 12's cancel, the natural logs cancel, so I'm left with t equals natural log of 20 all over 12 times the natural log of 1.0075. Right, so there's my exact answer. So then to get my approximate answer, I could plug that in my calculator and get 33.41. Right? So if you put $25,000 in this account and leave it alone, it'll turn into $500,000 in 33.41 years. Right? All right, so then this next bit is just, something I found interesting that you can read over, but it's a Blitzer bonus, so you can read over that. And if you actually go into the textbook, these links you can click on, like this world with a click, and it will take you like to a website or a video, so it's kind of interesting to explore, right? So you can read over that and look over that if you'd like. And then now I just have one last example. So we're already at an hour mark. So to save time, I have the solutions for this posted, and it's really very, very similar to the example we just did. So I'm just going to tell you the answer you should get is 14. And you can look at my work posted on Canvas. If you look at the section 4.4 notes key under modules, you could look at how to work that through, right? So then what I want to do is look down here at the solve by graphing. So how to solve this by graphing is you can let y1 be one side of the equation and y2 be the other, and then where the graphs intersect are going to be the solution or the solutions, right? There could be more than one. So if I So I think for this example, I'm going to get my larger graphing calculator, the one I've used before. All right. So I'll just show you real quick how to find those solutions. All right. So for the first one, we would put in, let me just clear these, and I need to turn this plot off. All right, so we want to put in e to the x, so second e to the x into y1, because that's on the left-hand side. On the right-hand side, we have minus x. So I can look at the graph of this. So let me change my window. Let me try going zoom standard, see if that looks nice. Yeah. So here's the equation, right? Both graphed. So then the solution is going to be the intersection, well, the x value of the intersection, right? Because that's what we're worried about. Right, so I just did second calc intersect, and then now I can estimate for the first curve, estimate for the second curve, and then try to guess, and it will give me the values, right? So this x value, this negative 0.567143, that is the solution, right? And we only report the x value here because that's what we're trying to solve, right? Solve for x. That's the only variable in the equation. Right, so that's all there is to that first one. And then to solve for the second one, we would put in, e to the x. Oops, I could have just left that, right? E to the x plus the natural log of x. I could put that into y1, and then for y2, I just need to put in 4, right? So I put the left-hand side in one of the y's and the right-hand side in the other, and I can look at the graph. and then calculate the intersection, right? So second calc intersect, and then we're going to guess on the first curve where the intersection is, so try to get close, and then on the second curve, and then guess again, and then there's the x-coordinate, right? So again, just the x value is the solution, the 1.315. That's the solution for that equation. So this solve by graphing is useful, like if your equations are like really complicated. It's kind of like a last resort that you can get, try to get a reasonable solution, right? So it's another technique. All right, so around an hour and 5 minutes. That's plenty of time for this. If you have questions, be sure to ask. Thanks for watching.